Okay guys, in this video we're going to start talking about section 5.3 and by start I mean start and finish, right? We should be able to get through the entire section in one go. So let's get started. We're going to talk about alpha beta pruning, and alpha beta pruning is going to be a way for us to speed up the search, right? The search for contingency plan for deciding what move we're going to make next, right? So essentially this thing is going to be a modification of the Minimax algorithm to try to cut out unnecessary subtrees, right? And so in the previous video I gave you kind of a hacky little thing where you could skip some subtrees just by saying let's end this loop, right? And that's part of the max or the min if we know for a fact that the utility value we've gotten back is going to be the best that we can get, right? The utility value that has been carried up through the recursion tree, right? If we know for a fact that's the best value we're going to get, well then stop looking. Right, now that worked great tic-tac-toe. If we scored 1 for a win, 0 for a tie, -1 for a loss, one state that's worth 1 is as good as another as far as we can tell, or for tic-tac-toe, so fine, go with it, right? But for something a little bit more complicated than that, it's not necessarily going to work. Right, so anyway, alpha beta pruning is another attempt at speeding things up, and that's what this section talks about, and also provides maybe building on alpha beta pruning to try to speed things up even faster. A lot of what you're doing in AI is a battle against time and the use of resources. Okay, so let's dig into it. Okay, so now remember, Minimax, that type of searching, very bad, very inefficient. Right? We talked about that last time. Horrific. Whatever we can do to speed up the search, we want to do that. Okay, so it's possible to cut that inefficiency, right, by quite a bit. So how? Right? Try to figure out what the best decision is without expanding all the nodes. Right? If you can do that, then you can eliminate potentially whole subtrees from the search tree. Right? The more you eliminate from the search tree, the more nodes you eliminate from the search tree, the fewer nodes that you have to create, right? The fewer that you have to examine, and so the less time it's going to take to find your actual solution. So how? Right? So what we'll do is we'll use another form of pruning that allows us to ignore subtrees or parts of the tree. Right? I gave you kind of a hacky way with tic-tac-toe in the previous video. It's not always going to work, right? It was a slight modification that I suggested to Minimax. Here's another one, okay? And this particular technique is known as alpha beta pruning. Okay, so let's dig into it by looking at this figure that illustrates how this works with a simple example, right? So the alpha beta algorithm keeps track of the best values for min and for max from Max's point of view, right? Scored in terms of utility values from Max's point of view, right? So the algorithm gets its name from keeping track of the best values so far for max, right? That's the alpha, and the best value so far for min, and that's beta, right? So keeping track of best value so far for max, best value so far for min, max, alpha, min, beta. Okay, so best value for max so far, the alpha value is the first one in the square brackets. The best one so far for min, second value in the square brackets. Initially, when this when this algorithm starts, it's passed the smallest possible number for max and the biggest possible number for min. So smallest number for alpha, biggest number for beta. Okay. Now remember, the right side up triangles represent this theoretical node for max and upside down for min, right? So start off, and max has to consider 3 possible actions, right? So the first action would lead to a min node being generated, labeled as B, right? Now, min, as a result, is going to consider 3 possible counteractions, right? So the first action that it considers would be one that leads to a terminal state that has a utility value for max of 3, right? So that's the best move that it's found so far, right? So that value 3, okay? But then we move over to the drawing labeled B here, and it evaluates another action. And that particular action leads to a state that's valued at 12 from max's point of view, right? So that's not better. And so the beta value is not getting updated, okay? And then come down to C here, and min evaluates its third option in response to the first possible action that max could have taken, right? And that leads to a state that's valued at 8 from max's point of view, right? Now, that is definitely not better than the 3. So its beta doesn't get updated, right? The beta value doesn't get updated. And so now we know that the best possible value for max is also going to be 3. And so that's why that 3, 3 is labeled there. So the alpha and beta values, both 3, right? So that gets returned back up to the top of the tree. And so the alpha for max, the best move it can make so far is that 3. That's the best value, the best valued action it can make, right? So this first action valued at 3. Okay. Now it has to consider its second possible action. Okay. Second possible action. And this is going to get past the same smallest number, biggest number, because it's recursive. But the min node C gets generated, and now min has to consider all the possible moves that it could take in response. So the first move that it could take in response, the first possible action it could take in response to this new action by max, would lead to a state that's valued at 2 from max's point of view. Now at this point, min's like, okay, that's good. So let's go ahead and set up our beta at 2, right? But from max's point of view, now remember, this is max trying to figure out what move that it wants to take. It knows at this point in the algorithm that max knows that there's no way that min is going to choose anything worse than that 2, or let me rephrase, anything that min chooses, right, is going to be no more than 2, right? So for this second and this third action, let's say that this second action leads to a state from max's point of view that's worth 50. Well, there's no way min's going to choose that one. It's going to stick with the action that leads to the state for max that's valued at 2. Okay, so let's say that that third action that min could choose leads to a state valued for max of 100, right? Well, there's no way min's going to choose that one either. Therefore, it's pointless to continue evaluating those actions, because that 2 is going to be worse than what we could have gotten by sticking with the first action. So it's over, it's done. We don't have to expand these other nodes, right? And if those nodes were root nodes for other subtrees, we don't have to expand those subtrees either, right? So we're done with that subtree. We're done with the subtree whose root is the min node C, right? So at this point, max knows it's not choosing that second action, right? worst, it's going to choose the first action. Okay. Now, there's one more action it has to consider, and that's the action that leads to min node D. And so, any one of those actions that min could take in response potentially could lead to a state that's better than the first action would lead us to, that would lead max to, right? But you won't know until you start expanding those nodes, right? So max continues the search, says, all right, well, if min takes that first action, where's that going to lead? Well, that's going to lead to a terminal state with a value of 14 from max's point of view, okay? But there's still two possibilities left here, two possible actions that could be worse than the first action, which was valued at 3. So we'd have to continue the search, max would have to continue the search, expand this second node, right, the second terminal node, evaluate the second action that min could take, and that second action would lead to a state valued at 5 from max's point of view, right? But there's still one more action it could take that could be worse than the first action that max took, right? Its first possible action that it could take, I should say, right? So after expanding that terminal node, that corresponds to that third possible action that min could take in response to the third possible action that max could take, we find that it's valued at 2 from max's point of view, right? So what that tells us is that of the 3 actions that max could take for the first state represented by max node A, the first action is going to be the best in its interest, right? Because that leads to the highest value terminal state that would result from a counter move chosen by min. Okay, so it's going to be better than anything that min would choose in response to the action that leads to mid node C. It's going to be better than anything that min would choose in response to the action that max took that led to min node D. Right? So here's another way of looking at it. Max is going to take that action that leads to the best utility value in response to everything that min could possibly do. So this first line right here corresponds to the evaluation of min for all the possible states. One state was worth 3, one was worth 12, one was worth 8. That was that first subtree, right? The second subtree, min is going to choose an action that leads to the smallest possible value, right? So 2 or X or Y, right? But remember that max is going to choose that action that leads to its best value, right? So that 2 in that second subtree, min's going to choose that at the worst in terms of from min's point of view, right? Because if, like I said, if X was 50 or if Y, if that node was worth 100, there's no way min's going to choose those in response to max's action. So I go with the 2, and then similarly for that last subtree, right? So max is going to choose that action which is the biggest of the first action's value, the second action's value, or the third action's value, right? So it's going to be a toss-up between, it's going to choose between the biggest of 3, Z or 2, where Z is at most 2 because of, you know, what I just said, right? So that's going to lead max to choose that action that's valued at 3. Okay. All right, so another way of looking at that is, look, you know, if you are in a subtree, if max is part of its search comes across a subtree for a node labeled M that has a certain value, right? If that's better than the node in some other subtree, right? It's not gonna go with that other node N, right? It's going to take the action that leads you down into the subtree that has that value, M, if M is better than N, right? That move that could lead you to the subtree, down the subtree, eventually through the path going through that N node, it's never going to happen, right? Okay, it works in part why? Because of depth first search, right? I mean, if you're, as we're going through doing the depth first search, you know, you're moving down one subtree, valuing that subtree, backing up, going into another subtree, backing up, going into another subtree, right? And so you can abbreviate, or you can cut short the depth first search down one subtree and back up early, right? That's what that means. Okay, so how can we tweak this algorithm to make it execute even faster? Well, consider the order in which you consider actions or moves, right? So the order in which you look at states can have a huge impact on the performance, right? Depending on the values of those states, that's going to determine if you have more or less nodes, right? So let me go back up to this tree, right? Let us say that for this third subtree, okay, that first action led to a state that had a value of 2. Well, then the other two states, which were valued at 14 and valued at 5 respectively, they would never have gotten expanded. They would never have gotten looked at. Those nodes would never have even had to been considered, right? So just by changing the order in which you're considering the actions can speed up the execution of this algorithm even more. Okay. All right. So anyway, so some numbers for you. I'll just run through this really quick, you know, because you can read this on your own. But begin the examinations with those successors which are most likely going to be the best, right? So going back up, in this first subtree, we started an examination of a node that was most likely going to be the best, right? 3, okay, or 2, okay. Allows you to cut off these extra pieces, right? Prune these extra subtrees. All right. So if that's the case, then alpha beta only needs to examine big O of B raised to half M nodes, right? Where B is the branching factor, okay? Minimax is going to need big O of B to the M, all right? Now, essentially what that means is that that branching factor becomes square root of B instead of B, right? So by doing alpha beta pruning, chest's branching factor goes from something like 35 to 6. Okay, remember what branching factor means. That means how many child nodes have to get generated. That's a huge increase in speed. Okay. All right, so the algorithm is implemented using 3 functions. You've got your first driver function, alpha-beta-search, accepts a state that the AI has to come up with a move for as an argument. It can return the action, the move that it should take. Okay, that function starts off by calling max value, you know, the max function, passing it the state, and for alpha, it's passing, you know, the smallest possible number. For beta, it's passing the largest possible number. Remember, this first number here is for max. This second one right here is for min. Okay, you're going to return that action of all the possible actions that has the matching value, right? It has the best value. So remember the actions function, you pass that state, returns all the possible actions for that particular state. So we're looking for an action where it's going to return an action that matches the best value V. Okay. All right, so let's look at the max value function, right? It's accepting the state, the alpha value, the beta value, can return the a utility value that is a value for the particular state. Its value from Max's point of view starts off with the base case. If the terminal test for a state is true, that means that particular state that Max was passed, if that's terminal, awesome, done, function's over. Return the utility value of that state. Otherwise, evaluate each of the actions in turn. Right? Start off with value V set at the smallest possible. Now for each action A possible from that state, do what? Find the biggest value, right? Either the value that you started with or the biggest value that min will give you, right? So the biggest value that min will give you. So that value that min will give you is going to be the value of the state which min decided is the least harmful to min, right? It's going to choose that value which is the least beneficial, the value for the state. It's going to choose the action that leads to the state with the smallest value from Max's point of view. Okay? Now, if the value is greater than or equal to the beta value, well then just go ahead and return it right freaking now, right? So if what we found so far is better than anything that min would give us, right? Than what min would give us, what we found so far, well then you're done, right? Cut it off. There's the cutoff. Otherwise, the alpha value is going to become, or is going to be replaced with the bigger of the two, right? Bigger of the alpha that we've seen so far, or the value for the actions that we have examined so far. Okay. Now, min, that min value function, is doing the same thing, just the opposite, right? It's equal but opposite. So this is working from min's point of view. This local variable v gets set to the biggest possible number. It's going through and evaluating all the possible actions that could be taken from that state. It wants to find the smallest value, the smallest valued action that leads to a state that has the smallest value for Max. Okay, so if you ever have a value that is less than the best thing for Max, go ahead and return it right now. Right? Don't worry about learning anything else or looking at anything else, right? So this corresponds to, you know, when we cut off this second tree, right? Look, we found 2, right? That's already going to be better than anything we've seen so far, right? So Max's point of view, way back up here at the top of the tree, is 3. Well, that 2, for min's point of view, is going to be better. So go ahead and return that. It's over. Okay. There's no reason to look at these other 2. Okay. So that's how that cutoff works. Right. Otherwise, you know, replace the beta value with the smallest of either the beta that you've seen so far, or if you found an action that leads to a state that's even less valuable, return or replace beta with that value. Okay. All right. Okay, so let's look at that previous figure again in a slightly different way. I've put up for reference the alpha beta search algorithm on the left here, and then the previous figure on the right. So I figured we'd kind of sketch it out, trace through it from scratch. I won't do the whole thing because it'll take way too long, but we'll get it started, and then you can finish it on your own, just to see it kind of how it works. So when you invoke this function, the search function, right? When you start the algorithm, you'd be passing to it some state, right? Let's call that state A, right? That'd be the argument that you pass, and this is going to return some action that the AI should take, right? Maybe putting X in a certain square, right? Maybe moving a piece across the chessboard, right? Whatever. Okay, now the algorithm then next calls max value, right? And it has its own, that driver function has its own V function, which I'll call V sub 0, right? And we're passing to the max function state A plus for alpha, the smallest possible number, and then for beta, the largest possible number. Okay? So that causes a max node to be generated. Okay? Max node to be generated, the max value function starts executing. Now is that a terminal state? No, it's not. We know that from the diagram. Okay. So that max value function now has its own V come into existence, which I'll call V sub M for, maybe I should call it V sub X. That's what I'll do. I'll call it V sub X for max. Okay. So that gets set to negative infinity, the smallest possible number. Now for each action possible from A, I'm going to do these three things. Okay, so call the first action A sub 1. Okay, now you're going to replace V sub X with the smallest, or excuse me, with the biggest of what's already in there, or whatever value that the min value function returns. Okay, now we're going to pass to the min value function the result of the state A with action A sub 1 applied to it. So that'll lead to state B. Okay? And then we'll also pass alpha and beta. Okay? So that's going to cause a min node, but they're being passed the B state. Okay, so now the min value function takes over. Is B state a terminal state? No, because we know that from the diagram. So then it has, that min function has its own V, right, which we'll call V sub n for min, right? Now for each possible action that it could take from that state B, it's going to do some stuff, right? So now we know that B plus action B sub 1 leads to a terminal state based off of the diagram, right? Because of this guy right here. So the max value function gets called, the resulting state plus alpha and beta gets passed to max again, but we know the first thing that's going to happen is that it's going to hit its base case terminals. Terminal test is going to say, yeah, that state is terminal state. Okay, so I won't even label it, and it's got a utility value of 3. Okay, so max value returns 3, and we're back in the min function. And so max value return 3. So what's smaller? What's in its V? Right now, I forgot to write it here. Right, that V before the loop started was infinity. So what's smaller? V infinity, or what max value just returned? 3. Well, the 3 is. Right. So that V for min has now got 3 in it. Okay, now, is V less than or equal to alpha? No, 3 is not less than negative infinity, so you're not returning V, right? So now you're going to replace beta with the smaller of what's in beta, infinity, or what's in V, 3. So what's smaller? 3. Okay, now you go back up to the top of the loop, and you look at the second possible action. B sub 2, right? Now, action B sub 2 applied to state B is going to give you a new state that's terminal, just like the previous state, right? So we pass that plus alpha beta to the max function. Max function automatically triggers its terminal test, and it returns a utility value of 12, right? So that 12 goes back to the min function. Right? So what's smaller? What's in V or what max value returned? Well, what's in V? So that doesn't change. is v less than alpha? Less than or equal to alpha? Nope, 3 is not less than or equal to negative infinity, so we don't return. Now beta gets replaced with whatever's smaller, what's in beta or what's in v, right? Well, they're the same, so that remains unchanged. So that iteration of the loop is done. Next iteration of the loop starts. There's one more action that can happen, v sub 3. Now just like before, the thing's going to play out the exact same way, terminal node, but the value for that is 8. Right? And come back, max value function returns 8. What's smaller? What's in v or 8? Well, what's in v is, so v is going to remain unchanged. Is v less than or equal to what's in alpha? No. What's smaller? What's in beta or what's in v? Well, they're the same, so that remains unchanged. So the min value function returns what's in v, and that's 3. So it returns 3. Okay, so remember, now we're back up to the max value function, and the max value function has its own v, and so the min value function just returned 3. So which is bigger? What's in v, negative infinity, or the 3? Well, the 3 is. Okay, so then max value continues on. Is v greater than or equal to beta? Is 3 greater than or equal to beta? No. Okay, so then move on. Alpha, what's bigger? What's in alpha, negative infinity, or what's in v? 3. Well, v is bigger, so alpha becomes 3. Right? And so the next iteration of the max value function starts, which is going to get you action a sub 2. Right? And so similar thing's going to happen. V is going to replace with whatever's bigger, what's currently in its v, which is 3, or what the min value function returns. Well, the result of applying a plus a sub 2 is state C. Okay, so that gets passed along with alpha and beta, 3, 3, to the min value function. The min value function starts executing. Its v has got positive infinity. And then for each action in C, right, lather, rinse, repeat what we just did. So we're going to find the minimum of what's in its v and, or excuse me, what's in its v and what was returned by max value. Right? So call max value, but we know that that's going to be a terminal state based off of the diagram. Okay, so we call max value, passing it, state C plus alpha and beta, but it's going to hit the terminal test. What's that terminal state's value? We know from the diagram that it's 2. Okay, so min then is going to place in v the smaller of what's already in its v, which is infinity, or what max just returned, max value just returned, well, max value just returned 2. So what goes in there is 2. Now, is that 2 less than what's in alpha? No. So then what gets placed in beta is the smaller of what's in beta or v, right? So what's in beta? 3. What's in v? 2. So that becomes 2, right? So I think I'm going to leave it there. I've gone through the algorithm, traced through it with you, got you started. I'll leave it up to you to finish it off to see how the algorithm works. But there's an example of doing hand tracing, getting you started with it, showing you how alpha beta gets going, jumping back and forth between max value and min value. Finish this off on your own, and then you'll really have a good feeling for why this works. Now remember, these two actions right here basically aren't going to execute at all, right? You're not going to even deal with these things. They're going to get cut off. They're going to get pruned. Okay, so all right, so go ahead and work on that on your own, and see how it turns out for you. Okay, so Just a couple more things here to finish it off. Just a couple points, just something to think about without going into too much detail. You can have move ordering schemes that can improve the overall efficiency even more, right? So you can have schemes that are dynamic, right? What does that mean? That means that, you know, if you had moves in the past that were the best, right, then try evaluating those first in the searches. Okay, now those moves have a name. They're often referred to as killer moves, and trying to evaluate those killer moves, trying to use them first in the search, that's referred to as the killer move heuristic. Okay. All right, so, you know, modify search on the fly based off of moves that have been best in the past. Okay. Right, so certain games, transpositions can absolutely destroy efficiency, performance. What does that mean? What's a transposition? Certain moves, certain actions, they're just mirrors, right? So chess pieces, right? So if you have action A1, B1, A2, B2, that would mirror actions A2, B2, A1, B1. So, you know, you could move a pawn in a certain sequence. You could move a pawn, then a knight, and they end up in their spaces. Or you could move the knight and then the pawn, and they still end up in their same spaces, right? So pieces are ending up in the same position, just the order in which they moved was different. Okay, so one thing that you can do to cut down on searching situations where you have those nodes that are basically just going to be containing states that are mirrors of each other, keep what's known as a transposition table, right? So you can keep a table of moves that are similar, and that can allow you to ignore those duplicates. So basically, think about the explored list from graph search, right? So as you're going through, considering actions leading to states, hey, if you've already seen this state in the search already, toss it, right? You know, if we've already seen a state where you've got the king and the queen in these two squares, who cares how they got there? The king and the queen are in those squares. So we've seen this before. We don't need to generate a whole nother subtree off of it, right? Just use the previous subtree to determine what the best action is going to be. All right, so that brings the discussion on section 5.3 to a close. Alpha beta pruning, right? So big thing with it, look, you're keeping track of the best move you've seen so far, and that's going to allow you to eliminate whole subtrees, because you're able to say, look, you know, there's no possibility that Min is going to choose an action that's better than the one that it's seen so far, and that particular action that Min would choose is going to be worse for Max based off of what Max has seen so far. So just forget that action, forget that subtree, don't even worry about it, cut it off.